So one more time, we have f of x to x minus 1, and we have f inverse, which is x plus 1 over 2. You already told me that this is linear, so then we need two ordered pairs, the x and y intercepts, to graph them. So as we know, when x is 0, we determine y. When y is 0, we determine x. So when x is 0, how much is y?
0.
One more time. When x is 0, how much is y?
Negative.
Very good. So 0, negative 1 is the first ordered pair. Now when y is 0, 0 equals 2x minus 1. I move on to the other side, and I get that x equals 1/2. So the two ordered pairs are 1/2 comma 0. We're going to graph 0 comma negative 1 and 1/2 comma 0. Would you agree? Do you agree with the x and y intercepts? Yes? Okay, I'm going to graph. This is the original function. F of x equals 2x minus 1. Before we continue, I need my tent up. Before we continue, we have to talk about the following situation. If the function takes 1, let's say, to 10, what would the inverse function do? Will take
10.
back to? So if a point of the function is 1 comma 10, can you give me a point of the inverse function?
Just swap the numbers.
Exactly, that's all I want you to say. We have two ordered pairs. Please give me the two ordered pairs corresponding to these two for the inverse function.
So you would expect also, since this original line has a positive slope, that the inverse would have a negative slope.
No,
No?
no. If the function is increasing, the inverse will be increasing.
Okay.
So give me two ordered pairs, please.
0, 1 over 2.
Excellent. So the reverse, the opposite, I should say, and I'll explain what it is opposite to, is this. Excellent. I need one more.
0, negative 1 over 0.
Excellent. Negative 1 over 0, which is this one, opposite to that. Before we graph the inverse function, we must graph something that always has to be there when we graph the function and its inverse on the same coordinate system, which is this line, which is y equals x. So when we graph the function in the inverse, we will reflect the graph with respect to y equals x. Now I can graph it. One piece of advice. If the function crosses y equals x at this point, the inverse function has to cross at the same point. How come? Because points on this line are 1, 1, 2, 2, 3, 3, 4, 4, reverse 3, 3. What do we get when we reverse 3, 3? 3, 3. So if the function crosses, let's say, at 2, 2, the inverse function has to cross y equals x at 2, 2. So here it is. This is the graph of f inverse, x plus 1 over 2. I don't ever bother to find ordered pairs for the function from scratch because I have two ordered pairs for the function. For the inverse function, I don't care to determine points. I already have them. If I have this for the function, then this is for the inverse. If I have this for the function, that's for the inverse. And they are always symmetric, the function and the graph of the function and the graph of the f inverse of the inverse function. They have to be symmetric. My graph may not be perfect. They have to be symmetric with respect to this line, y equals x. They have to overlap. This piece with this, and this piece with that. That's always the case for any two inverse functions graphed on the same coordinate system. Is this clear? Yes?
So even if you're dealing with a quadratic, you're still going to have the same property?
It's not one-to-one?
Oh, so you're right.
But it's a perfect question. Let me give you an example. Thank you for saying that. Excellent. So let's say, and we did graph. Thank you, Bob. At some point in time, we graph this for transformations, right? What is this graph?
Quadratic.
X squared. Good. And then I'll say, okay, let's find the inverse. And you have to say, sorry, you can't, even if you try. It's not one-to-one. And then I'll say, okay, I'm going to make some changes then. I don't want you to determine the inverse of that function. I want you to determine the inverse of x squared only for x greater than or equal to 0. And you can say, okay, now it's one-to-one, and I will be able to find the inverse. But we say we truncated the domain. I restricted the x, exactly. So even from a non-one-to-one function, if I choose my domain the way I wanted it to be, I can create a one-to-one function. So in this case, you said, what about x squared? And I said, okay, on all real line, I can't, because it's not one-to-one. But if I do this, I can find the inverse. Perfect. And now if you would like, let's graph it. I don't know what the inverse is, but I can graph it. It crosses the same point. Here it is. I don't know what that is. Of course, it's the square root of x, right? With the truncated domain, of course, and range. A range is still the same thing. But, so this will be f inverse for x greater than or equal to 0, of course. So even from a non-one-to-one function, I can create a one-to-one function. I can create its inverse. But always remember, what has to happen is, when you graph them on the same coordinate system, they have to overlap. This piece with this piece, this piece with this piece. If x squared crosses at 1, 1, and the inverse function has to cross at 1, 1. Perfect. Thank you. Thank you, Bob. Well done. Okay, now the last two functions, in addition, quadratic function, we have to go back to it and graph it and so on and so forth. But the last two new functions that we are going to look at are exponential and log. So let's see. Exponential functions. Exponential functions. What do you think an exponential function? Why is it called exponential? Because it has an exponent, and the variable is the exponent. So here's how it looks like. A base, and x, the variable is the exponent. A is the base, and this is the variable, is the exponent or power. Okay, here's a sequence of questions for you. Can I raise 0 to the third power? Perfect. Can I raise 1 to the fifth power? Good, excellent. Can I raise -2 to the third power? Excellent. These are not allowed for the exponential function. They're all possible. In other words, the point I'm making is A cannot be 0, A cannot be 1, and A cannot be a negative number. Not allowed. Never. Okay, but what can A be? A can be two different things. It can be a number greater than 1, not 1, or it can be a tiny number between 0 and 1, not 0, not 1, and not negative. And I'm sure Bob will ask immediately why. And here's my answer. Only because we would not be able to define the inverse function. The inverse function of this must have the same base. And there is no log with base 0, 1, or negative. That's the only reason. We wanted to have this function, and when you graph it, you'll see it's a one-to-one function. So we wanted it to have an inverse. But it's not allowed. 0, 1, and negative numbers are not allowed as the base. For that reason, just that reason. Okay, we're going to look at two different situations: an exponential function with a base greater than 1, an exponential function with a base less than 1. We're going to graph them and take it from there. Look at the transformations, etc., etc. I promise these are the last two new functions for the semester, and we have to go back to the quadratic, and that will be the end of the material for this course. It's a lot in 7 weeks. Don't mention it to anyone, but that's my opinion. Okay. So let's take a look. Let's say a simple exponential function with base 2. 2 raised to the x. What I'm doing in pre-calculus in 15 weeks is a lot. Okay. So let's take a look at a table with ordered pairs. What do you think? I'm not talking about the base. What do you think the power can be? Base is 2. Can I raise 2 to 0? What do I get?
1.
Excellent. Can I raise 2 to the first power? What do I get?
2.
Excellent. Can I raise 2 to the second power? What do I get? 4. So this way it goes, fine. Can I raise it to negative 1? 2 raised to negative 1. 2 raised to negative 1, we know this represents. Exactly. Let's raise it to negative 2. Excellent. So obviously this is a nice, friendly function. Why? What is its domain? Exactly, friendly function. So exponential is defined on negative infinity to infinity. So this is domain. Any exponential, this is the domain. And in a moment, we will write the range. I don't have it yet. We have to discuss it first. I don't want to divulge it yet. Okay, so let's take a look and try to find the range this time. So I'm going that way. 1 over 2, 1 over 8, 1 over 16, 1 over 132. I'm sorry, 1 over 32, 1 over 64, 1 over 128, 1 over 10 million, 1 over 10 billion. Which direction am I going?
So it's approaching 0, but not really hitting 0.
Excellent. That's exactly it. So it's approaching 0. Excellent. This direction now. 2, 4, 8, 16, 32. Where is it going? 2? Excellent. So can anyone tell us the range now? I want to put it in here. Careful. We're talking about the function values. That's it. Good. So let's graph the function now. Can anyone give us the first ordered pair from left to right? The first ordered pair is from left to right. Right. kind of difficult for me to plot, but I'm going to say that. Next ordered pair.
-1/2.
Very good. Next ordered pair.
0, 1.
Excellent. Next ordered pair.
1, 2.
Very good. Excellent. Next ordered pair. Excellent. The fastest growth possible, exponential. Now, I'm not saying with base 2, but I'm saying the fastest growth from all functions we looked at. Okay, is it 1-to-1? Good, which means that you're going to give me several ordered pairs so I can graph the inverse. Because if it's 1-to-1, it has an inverse function. I want to graph the inverse. Please help me here, graph the inverse. Yes?
1/4 to -3.
Great job. Excellent. Next point.
1/2 to
Excellent.
1 to 6.
Excellent. One more.
2, 1,
2-1. Excellent. Here it is. F inverse for 2 to the x. If the function is increasing, the inverse function has to be increasing. We don't know what this is, but can you identify the domain and range for me? So the inverse function of the exponential will have which range, which domain? What will be its domain? You either look at the graph or you say this. One or the other. What will be the domain of the inverse function?
So then it's approaching 0, but not really touching.
Exactly.
So 0 is approaching 4.
This must be the domain of the inverse. What is the range of the inverse? Right. This must be the range of the inverse. Mandatory. For the same reason that you told me 1 goes to 10 and 10 goes back to 1. So this domain, this range, and they are reversed for the inverse function. Agreed? So what will you conclude immediately about the inverse function of 2 to the x? Is it friendly or not? Not friendly. It's not defined everywhere. This is friendly. I don't ever have to think or worry about the exponential function. But its inverse, it joins the square root and 1 over x. Those are not friendly functions. The square root will not exist if the quantity underneath is not positive or 0. The rational function will not exist if the denominator is 0. Same thing here. The inverse of this exponential will not exist for any number to the left of 0 or 0. Any questions on this? Okay, this was just one shape. Let's look at the other shape, the second shape. So let's say f of x, 1/2 raised to the x power. How come that this is the second shape? It is the second shape. This is the second possibility. In this first situation, we had the base greater than 1. In the second situation, second possibility, I have the base between 0 and 1, like, for example, 1/2, or 1/4, or 1/3. I chose 1/2. Doesn't matter. Okay, what is the domain of this function, please? Of course, excellent, because we know all exponential functions are friendly. I don't have to ever worry about it. Excellent. I'm going to use the same numbers from before. So let's replace x by -2, and then by -1, and then by 0 by 1, and determine these y coordinates. Can anyone give us the answer when we replace x by -2, meaning 1/2 raised to -2? Squared.
2 squared.
Very good. Awesome. Indeed. With -1. Excellent. With 0.
1.
Excellent. With 1. Great job.
1/2.
Of course. With 2.
1/4.
Excellent. I want to see this direction and I want to see this direction. 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/128. Where am I going?
0.
Excellent. The other direction. 1, 2, 4, 8, 16, 32, 64, 128. As expected, right. Good. So let's take a look. From left to right, please, anyone give me the first ordered pair I need to plot. Excellent. Next one. Very good. Next one. Very good. Next one. Very good. And 1/4. You have to trust me. Of course, it's not 1/2. My graph cannot be perfect. Graphing 1/4 and 1/2 is not easy. But definitely this is 1/2 to the x. So as we notice, when the base is less than 1, the function is no longer increasing but decreasing. Is it 1-to-1? Yes, it is 1-to-1. I want to graph the inverse function. I need your help. I know one point for sure. Which one? It's a must. If the function crosses y equals x, the inverse function will cross y equals x at the same point. Mandatory. So just give me several points so I can graph this. Good. Careful. 1/2, 1, and 1/4. 1/2. Yeah. This is the inverse function of 1/2 to the x. This piece is here reversed or reflected. This piece is here reflected with respect to y equals x. Questions? Questions? I would like us to, before we evaluate a couple of exponential functions, there are two very important exponential functions. I would like us to graph a function with transformations. I'm going to make one up. So let's suppose f of x equals 3 to x minus 1 plus 3. What is the base function I used here? Because it's not the square root and it's not the absolute value and it's not x squared. But which function did I use now? I used the function 3 raised to the x. It has an exponential, it has to have a variable, right? 3 to the x. What is the first transformation on 3 to the x? It must be 3 raised to x minus 1. But what does it do? What does 3 raised to x minus 1 does to 3 to the x? Remember, the first thing you have to identify whether it's a transformation on x or a transformation on y. Are we changing x or are we changing y? Perfect. Which direction? So now I identified it's x, so it has to be something to do with horizontal, not vertical. Yes, but which direction is minus 1? Careful. The -1 is to your right. So right 1. Good. Final transformation is on number 1. So what is the transformation on number 1? No longer on the base. This is a transformation on this, which is 3x to x minus 1 plus 3. What does this do to that? First, I have to identify whether it's a transformation on y or it's a transformation on x. Excellent. And that does what?
Raise it by 3.
Up 3. Excellent. Good. So when I graph 3 to the x, do I graph it like this, increasing on all its domain or decreasing on all its domain? These are the only two possibilities. Is it increasing? Do I graph it like this, crossing at 0, 1? Or do I graph it like this, crossing at 0, 1? Very good, because the base is greater than 1. Awesome. Good. Then you told me to move it right 1. So please tell me this point, which is 0, 1, where does it move? Excellent. Here it is. Here's the new graph. 3 raised to x minus 1. Great job. What happens next? Finally. Very good. See, I don't think that this section or chapter, that's my opinion, I don't think that they belong here. Because now I have to talk about something that we haven't discussed, which is what it's called the horizontal asymptote. So I have to move the horizontal asymptote up 3. So I disagree with presenting this material in this class, but that's me. So 1, 2, 3. 1, 2, 3. So now this is y equals 3. And this point moves up here 3 units up. 1, 2, 3. So this is the graph. This is 3 raised to x minus 1 plus 3. Now I'm going to ask you, what is the range of the final graph? You can no longer say 0 to infinity, because once it's shifted up 3 and we shift this horizontal line with it, now the range is different. What is the range? From
0, 3.
So we shifted everything 3 units up. So we can no longer start at 0. The graph does not start at 0. The final graph starts at 3. Is that clear? So 3 to x minus 1 is from 0 to infinity. When we shift everything up 3, now it starts at 3. Okay, no problem. Is that clear? The domain is still all real numbers because it's exponential. That will never be a problem with exponentials. But this time it involves transformations. And the transformations shift the graph up 3. So now the range is 3 to infinity.
So you're also saying you can never get a negative number out of 3 to x minus 1.
True, unless it has transformations. Let me give you an example. Excellent. Maybe you should teach this class, Bob. Please do. I'll sit down and rest. Because this is just, it's not a marathon. This is the sprint of my life with 7 weeks. Okay, here's an example. Thank you, Bob. Let's say negative 1/2 to the x and plus 4. Okay. So what is the base function here? That's not a function. To the x. Good. Now the first transformation is negative 1/2 to the x, and the second transformation is on number 1, negative 1/2 to the x plus 4. So what does this do to this? And remember, you first check whether it's a transformation on x or a transformation on y. If it's on x, you're going to tell me to reflect with respect to the y-axis. If it's on y, you're going to tell me to reflect with respect to the x-axis. Which one is it? Oh, I haven't gotten there. In order of operations, I have to multiply by -1 way before I add 4. I can't do that 4. I can't even look at 4. When you ask me to evaluate this for 1 or 2 or 3, I have to take 1/2 to the 3rd power, then I have to multiply by -1, and the very last step, I add 4. So compare these two. Is it a transformation on x or a transformation on y? -1 does not touch x. It cannot be on x. So it must be a transformation on y. So we reflect with respect to the x-axis.
Wait, you're talking about the negative sign?
That's the only change between this and this, right? So the first transformation is the sign outside. The second transformation is +4 of number 1. Number 1 plus 4.
I thought you were talking about the 1/2.
But you cannot multiply negative by 1/2. It has a power.
I thought you were talking about like the x and the 1/2. I didn't see the negative sign. I thought it was equal sign.
No, it's the negative. Okay, I see. Good, so we reflect with respect to the x-axis. Then, what happens to this when we get to the last step? What transformation is this from here, here? It can be on x or on y, not on both.
It looks like it's on x and y.
Exactly, up 4. Excellent. So let's graph. Now, question is, how do I graph 1/2 to the x? Is it increasing on all its domain? Is it decreasing on all its domain? It's a simple exponential function, but I need to identify whether it's increasing or decreasing. Yes, because the base is less than 1. And it must cross always, the original base function must cross at 0, 1, no matter what the base is. Then you told me to reflect this graph. Okay, just please give me where this point is moving to. And then I'll have the graph for you. Excellent. Indeed, 0, -1. So here's the graph now. This is the graph of -1/2 to the x. And now you want me to shift this entire graph where? Excellent. 0, 1, 2, 3, 4. Now please tell me where does this point go, and then I'll graph the rest. Excellent. So this is the final graph. I just wanted to re-emphasize it. So this is f of x, -1/2 to the x plus 4. The negative has nothing to do with 1/2, nothing to do with x. It's completely outside. Okay, so now the domain of this function no one can change. But look at the range. It's a totally different story. How come? Because of that reflection. It reversed the whole thing. It made it even negative as the outcome. So what is the range of this function now? From till? Exactly. Does that answer your question? So if we talk about pure exponentials, all your numbers, 0 to infinity, done. But once we throw in transformations, anything can happen. Not about the domain, though. The domain is carved in stone. At the core, it's still an exponential. It will still be defined everywhere. But when it comes to the range, anything can happen now, depending on what type of transformations we throw in. Very good question. Okay, now I would like to talk about two special exponential functions. Very special. Special exponential functions. Base 10, base e. So f of x 10 to the x, and f of x e to the x. The first one is called natural. I'm sorry, it's common. Natural is this one. Natural exponential function. And this is common exponential function. My apologies. Why are they so special? They have a lot of applications in real-life situations, but more, and also what is important, they are both increasing. And let's take a look at the graphing calculator. So let's graph these in y equals. See, they have their own keys right here. This in blue, 10 to the x, and this in blue again, e to the x. With blue is the second. I don't know if you have the second in blue, you can have some other color. So with the second key, e to the x, with the second key, 10 to the x. So we know what to expect. So when we graph natural log, second 10 to the x, and then we want to graph the other one, second e to the x. And you see in my software, I have the first one in blue and the second one in red, and I will use the standard viewing window. Here it comes. That's 10 to the x, closer to the y-axis because the base is greater. And here comes e to the x a little bit further away from the y-axis because e is smaller. It's 2.7. So they both cross the y-axis at 0, 1. Of course, we know that the calculator is lying. These two do not overlap y equals 0. Okay? So please do not copy something like this from the calculator, because we know that's not the correct graph. This is the correct graph for either one. Maybe eventually they get closer and closer, and they do get closer and closer to the y-axis, to the x-axis, but they do not overlap. So this is e to the x, and this is 1, and 10 to the x is this. Closer to the y-axis because the base is greater. Okay, I would like us to look at an application with exponentials, and this is the compound interest formulas. There are two compound interest formulas. They will be given to you. You don't have to memorize them, but I need to tell you what they mean. So, interest when we borrow money or when we deposit money. Compounded, recalculated. N times per year, and compounded continuously. Two different formulas. A equals P, 1 plus R over N raised to NT. I'll explain each piece in a second. And A equals P e to RT. So let's talk about this, and then I'll list the significance of each. P is the principal. So let's suppose we want to buy a home, and let's say it's $200,000, and this is the principal. Let's say we want to deposit $50,000. That will be our principal. So P is the principal in both cases, of course. P, principal. Either we deposit or we borrow. Uppercase A is the accumulated value if we deposit, right? Accumulated value, T number of years later. It can also be what we need to go back, get back, pay back when we borrow money, right? T, number of years. R, lowercase r, this and this, lowercase r, annual interest rate. And N, there is no N here, this is continuously, and this is N. Number of times the interest is compounded per year. Number of times interest is compounded per year. Okay, so let's have a scenario. Let's say we deposit how much money we would like to deposit. $1,000 into an account with an annual interest rate. What interest rate would you like? Well, what is available right now? It's possibly 2%. So let's say 2%. We cannot use 2%. It has to be changed into a decimal. Okay, let's say in how many years we would like to deposit this amount? 4. 7 years. And finally, how many times do you want? We're going to look at two different scenarios. One continuously, and the other one, how many times would you like the interest to be recalculated per year? Every month, every week, 4 times a year, twice a year? 4 times a year. We call that quarterly. Perfect. So then the deposit principal. So we want to know if we deposit $1,000 today at 2%, 7 years later, if the interest is compounded 4 times a year, what do we get at the end of those 7 years? So 1,000, 1 plus the interest rate 0.02, you said 4 times a year, raised to 4 multiplied by 7 years. One more time. Principal, 1,000, 1 plus, 1 plus the interest rate 0.02, number of times the interest is compounded per year, and then 4 times 7. The other formula will be for continuously times e raised to 0.02 multiplied by 7. No one can do this without a calculator. So let's determine those two amounts with a graphing calculator. And these are the compound interest formulas. So let's take a look. 1,000 in parentheses 1 plus 0.02 divided by 4, close the parenthesis, power in parentheses, I have 4 times 7, or you just write 28. It's up to you. Close the parenthesis for the top, and then press enter. And when we repeat for continuously compound interest, E in parentheses, we have the interest 0.02. Just want to make sure that I wrote R, not N. Yes. Okay. So 0.02 multiplied by 7. Close the parenthesis and press enter. So in 7 years, the first will give us 1,149.87, and the second one will be 1,150.27 at the end of 7 years. Any questions? And these are the compound interest formulas. Any questions? Any questions? So let's see what is left. So we have 4 minutes left for today. So here's where we are. Log functions, including common and natural logs. So we're going to talk about that. We haven't gotten to that. These are the inverse functions that we just graphed. The inverse. And then when we finish log, then we have to look at quadratic, the complex numbers, and 3 more methods of solving and graphing quadratic functions. So So, what would you like to do next? I know we have 3 minutes left. Would you like to, we already graphed. We're slightly ahead in the sense that we already graphed the log functions. But I haven't showed you what they mean and how they are determined. That part I haven't. Or we stop here because I'd like to talk to a couple of you about the first test. You want to stop here? You had enough, I'm sure. Yes, it's a lot. Okay, so let's.